So welcome back everyone to the afternoon session. So we'll have one talk followed by a discussion meeting. So it's my great pleasure to invite Dr. Jérémie Beck, who will talk about steering undulatory microswimmers in turbulence through machine learning. Dr. Beck.
Okay, thank you very much. So of course, I am indebted with the organizers for organizing this thing and giving me the opportunity to give a talk, and so it's up to now. So I'm sorry. I mean, of course, being at home means that one needs to one cannot refuse administrative duties. So I hope I will be able to follow as much as I can in the coming days. So basically, I'm going to talk about some work in progress, which is a work which was mainly done by two students. So Raphaël Chénaud, who was a master's student in my team, and Zakaria El-Khiati, who is starting a PhD. And this is also a collaboration with Laetitia Giraldi, who is a mathematician, a specialist of optimizing locomotion in Stokes flow. So basically, the motivation for what I'll be talking about are coming from different kind of applications, and I will focus mainly on one kind of things. So basically, these applications are trying to understand if one can get some good ideas from nature or machine learning in order to make some autonomous swimmers with applications to drug delivery, so of course aerial vehicles, but also to some smart sensors or catalysts that would be able to enter in industrial processes in places which are not reachable by humans. And so basically the inspiration from nature is of course coming from various situations that are known, observed in biological systems, such as low Reynolds numbers swimmers, where we heard yesterday many talks about that, but also optimizing flight in large Reynolds numbers for large Reynolds numbers objects, and of course collective and collaborative improvements of the displacements that are coming from interactions between different swimmers. So I will mainly focus on the case of microswimmers, with the idea of trying to understand if strategies are easy, if easy strategies can be found in order to design micro robots for drug delivery. So that's the main long-term focus, motivation that they want to develop. And basically, there are very specific things concerning micro robots that are sent in the human body. Basically, one thing is that such micro swimmers should be, so in addition to be efficient and targeted, basically they need to usually to go through very different media. So here is a picture of it's an artistic picture of a micro robot in a blood vessel. But you can imagine that from time to time, such a robot will have, after some trip in the blood, will have to go inside mucus in order to penetrate some specific places in the organ, and basically we're in different places where the rheology is changing a lot. So which means that it's going from Newtonian-like media to media which are highly non-Newtonian and from time to time active themselves. And so basically the idea is to design some strategy which will be able to adapt depending on the rheology of the surrounding media. And in addition, there is something which is very important for these micro swimmers, which is to be able to interact with the surrounding environment, in the sense that there are walls, there are maybe other cells like the red blood cells that you see here, or some other swimmers, and basically all these things make the problem pretty complicated. So basically, what I'll be talking about is which is one of the specificity of these microswimmers, which is the thing that the problem is twofold. So on the one hand, there is the problem of locomotion, which means that one needs to find some model, I mean some strategy, some gate in order to optimize the displacement of such objects. So basically, this is something which is usually done by looking at pretty complicated models, which are involving some elasticity, some free structural interaction, some modifications of the flow by the swimmer itself, and this is something which is done at the micro scale. And on the other hand, there is the problem of navigation, which is that given a given strategy for swimming, one needs to make the swimmer go from the place where it's released to the target where it's aiming at. And basically, then the question is more, depending on the complexity of the environment, is to find an optimal path or an optimal strategy in order to navigate inside this problem. So usually, because of considered applications, I mean, these two problems are treated in a separate manner because one is assuming that there is a sufficiently large separation of scales between the scale which are involved in the motion of the swimmers and the scale which are involved in the environment. And for the kind of micro robots I was talking about, actually, I mean, this large scale, this large separation of scale is not relevant. So basically, so this I talked a bit about these motivations. So the idea is to be able to treat situations where both locomotion and navigation are occurring at comparable scales. So basically, the scale of the motions, which will be like the motion or the size of the flagella, is comparable to the distance of the swimmer with the walls, to the distances with other fellows, then also to distances with all kind of obstacles, to possible eddy of sizes comparable again to this tail, and of course with the idea on the longer term to be able to address different rheologies. Okay, and the question is how to make optimal locomotion in such complex environments. So the model I want to discuss is a kind of super simplification of the what are called flagellated swimmers, so which are swimmers like, so here in the movie here what you see is a fish spermatozoon which is able to move by propagating a wave along its flagella. And so basically what I want to consider is this kind of motion which is called undulatory motion, which corresponds to being able to propagate a wave that is making the swimmer move with respect to its environment. So for that, what I will be using is the standard body theory, which is telling how to write the forces acting on a very thin fiber. So it's obeying what is called the Kosra equation. And so what is assumed is that this fiber is flexible, so with a given elasticity, that it's inextensible, and that it's interacting with the surrounding fluid only through a viscous drag. So basically, the equation of motion is written here. So it's a PDE, which is indexed by both time and the curvilinear abscissa along the fiber, and where the acceleration, I mean mass times the acceleration of the point x, of the position x on the fiber, is given by the viscous drag. So it's a non-isotropic viscous drag. So with a drag matrix which is involving the orientation itself of the fiber at these very specific locations, times the velocity difference between the fiber and the fluid at the position of the fiber. So it's very slender, so which means that variations of the fluid are supposed to be on scales much smaller than the thickness of the fiber. And then it's involving tension. So tension is just the Lagrange multiplier, which is associated to the inextensibility constraint. So which means that the fiber is not elastic in the longitudinal direction. And then there is elasticity, so which make the fiber relax back to a straight line. So it's just the usual Young modulus term. And basically what we are adding here is an active force, which is the thing that we want to control in order to make possible the locomotion. Of course, don't hesitate to interrupt me, because I will be happy to answer questions. So basically, these fibers have been studied in passive cases. So and they display some very specific properties. So for instance, they tend to in flows with the mean shear and boundaries, then they tend to align with the shear when the shear is strong, and to form and to stick, I mean, at the boundary, as you see these guys in the direction of the mean flow. So then when they are, I'm sorry, so when they are transported by a flow with structures, they tend to sample some specific regions. So as you can see, so let me replay it. This long fiber here at some point is captured by an eddy, and is then spending a long time rolling up in this eddy. Okay, so which means that they tend also to form some preferential sampling of the flow, and then they have their own deformation dynamics. So which means that, so for instance, when the fibers are compressed, they can go through a Euler buckling. So with the development of an instability of this kind. And of course, in principle, I mean, these fibers, if they are very long and very flexible, they can tie and create some all different kind of knots. And this is some recent work that was able to look at the statistics of this kind of knots. So basically, these fibers, so when they are passive, at least, I mean, they represent some kind of appealing prototype for a complex Lagrangian transport, because there is clearly a very complicated interplay between their own transport and the way they deform. So basically, now concerning the active locomotion force, I want to consider. So basically, I will be focusing on the simplest case, which is something which corresponds to planar undulation. So the force will be some planar wave, so some wave along a given direction that will propagate. So the wave will have a given wave number, and will propagate with a given velocity omega, and then with a rescale amplitude, and basically we will have a dimensionless parameter, this alpha, that will measure what is the amplitude of the force in dimensionless units. So in order not to cheat, so basically, so the wave is propagated along a given direction, and this will result in a motion in the perpendicular direction to this wave. So basically, in order not to cheat and to not to provide any input, net input of momentum to the motion of the fiber, basically we have to consider modes which are exactly integer modes of the fiber. And then, of course, in reality, in order not to have too much dissipation induced by rigidity of the fiber onto the dispersion of this wave. So basically, we are considering things where there is a relationship between the frequency and the wave number, which is such that the mode which is excited are exactly inertial eigenmodes of the fiber. So which means that once in principle, that once the mode is excited, basically it will continue to resonate. So here basically I will be mainly focusing on the overdamped case. So in the case where the friction with the fluid is very strong, so that inertial effects are negligible, but still I will consider that it's possible to leading order to excite such modes. So here what I show is measurements of the swimming speed resulting from the propagation of the application of such an active force in the absence of any external fluid. So basically I'm just integrating the Cosra equation. So it's not absence of external fluid, it's absence of external fluid flow. So basically, of course, there is a fluid with which, a fluid at rest surrounding the fiber, and basically what's happening is that because of the interplay between the forcing, the tension, of course, and this viscous friction with the external fluid, the fiber will be set into motion. And what you see is that the swimming speed as a function of the forcing amplitude has this kind of shape. So these are for different values of the wave number of the waves. So so from k equal 1, k equal 2, k equal 3, k equal 4. And basically, so what you see is that in all cases, the swimming speed is attaining a maximum for an order unity value of the forcing amplitude. So which means that there is no need to boost too much the forcing amplitude to swim sufficiently fast. So basically, it's sufficient to choose some values which are close to this maximum. Okay, and of course, in the absence of amplitude, there is no velocity. So so now concerning the kind of flow I will start with. So basically, I wanted to exhibit some kind of simple test case in which one could try to see how such undulatory swimmer is performing in the presence this time of an outer flow. So the simplest case that most of us are very often considering is the case of a two-dimensional cellular flow. So which means that so we are working in 2 dimensions. So basically the velocity field is incompressible and is deriving from a stream function, and this stream function is a periodic function in both x and y. So that's basically the space is divided in different cells this way, which are corresponding to vortices which are contra-rotating. Neighboring vortices are contra-rotating this way. And typically, so this kind of flow is characterized by 2 parameters: the size of the cell, so which is entering this periodic function, and the typical amplitude of the velocity that, for instance, we can measure at the place where it's maximal, which is in the middle of these edges. So basically, you can so from this problem, basically there are a number of non-dimensional parameters. So of course, the size ratio between the fiber and the cellular cell, which we will consider of the order of unity. So the inertia, which is measured by a Stokes number, which is involving the linear mass density of the fiber and the friction coefficients, and of course, which is written in non-dimensional units associated to the flow, so that we would expect to be very small compared to 1. Then the fluid flow intensity, which is how much large is the fluid velocity compared to what is the swimming speed in the absence of fluid flow, and the fiber flexibility, which is somehow the normal way, the usual way to non-dimensionalize the Young modulus of the fiber, and that we will consider very large compared to 1 because we want fibers to deform. So now we will consider the following navigation problem, which is we will put some fiber inside this flow, and we want to optimize the displacement to the right. So we want the fiber to go as fast as possible toward positive x. And so the question that we want to address is whether or not in such a simple situation, we can learn some strategy, some way to swim, some way to handle the fact that there are vortices, that there will be places with a headwind, and to see whether this strategy that we can learn from a simple situation will perform as well in more complex situations, so in particular in flows which are time dependent and with fluctuations of velocities and scale dependence. So basically, in the absence of strategy, so that these are two examples of swimmers which are trying to go inside this flow. So they just have no strategy in the sense that they are just trying to propagate a wave along the y direction in order to create this motion in the x direction. And what you see is that it's pretty complicated for these swimmers to do anything except by chance. So there are two aspects which are important in this case. Is that first they are swept by the flow, so they are unable to resist a headwind that will prevent them from going to the right. And the second thing is that there are directional reversals in the sense that because of the vorticity in the flow, they can. So yes, I'm materializing the head of the swimmers by this small point, and because of vorticity in the flow, I mean the head can be oriented in the wrong direction, and if they propagate the wave, so the wave is always propagating from the head to the tail, and so which means that in that case, if it's propagating the tail to the tail, I mean it will displace to the left, and so which means in the wrong direction. So what we have seen is that if we don't provide any strategy to these swimmers, I mean they will tend to just to diffuse in the flow stupidly, and basically not to achieve any mean displacement to the positive x. So the second thing that we see is that even if the cellular flow is known for non-being chaotic, so it's not chaotic for tracers in cellular flow, because of the complicated dynamics of the swimmers, so which are themselves obeying a PD, the Kostra equation. So in the full dynamic cellular flow plus swimmer is chaotic. So that's something which as we see can be maybe quite important. And then the next thing is from this observation is that in order to build a strategy, swimmers should know at least two things. The first thing is their orientation, so they need to know that they are facing the right direction. And the second thing is that they need to sense somehow the local wind in order to know when they are swept by the flow. So basically, based on that, so I will create I will propose some state and action spaces in order to write down some decision process for the swimming of the fiber. So the first, so the state space will have the following information. So it should be able to translate swimmer orientation, so knowing if the head is facing the right direction or not. It should know about the fluid velocity. So basically, the choice has been to know something about the fluid velocity at the head of the swimmer, and basically with a very stupid discretization of the velocity in 3 values. So negative values, values which are close to 0, and positive values. And then the last thing that we noticed was important is the swimmers should know whether it's buckled or not, because you see that if it's buckled like that, when propagating a wave along its body will not be very efficient in order to move, nor to unbuckle. So since we have 2 times 3 times 2 different possibilities, so basically our state space is a discrete space with 12 possible states. So concerning actions, so basically the action is simple, is just to choose the force amplitude and its direction. So knowing whether the swimmer is willing to swim vertically, so with 3 different amplitudes, to do nothing, or to swim horizontally with 3 different amplitudes. And so which means that to these 12 possible states, we can associate 7 possible actions. And now, so basically the game that we want to play is to find some policy, so some possibly optimal policy, which will correspond in a way to choose an action given the current state, so which can be seen, for instance, as the probability of choosing the action A given the state S. And so basically we want to find this kind of policy. So in the case where we have a deterministic policy, I mean, this pi of A will be a delta function centered on a given value of A for each S. So basically, since we have super simplified the configuration of the swimmer, so basically to 12 only possible states, which means that we have highly projected the full phase space, which is infinite dimensional, because we have, yes, Greg, I see that you raise your hand.
Can I ask a quick question?
Sure, you can, yes.
Describe, how does the swimmer choose the direction for its action? How does it choose whether to go vertical or horizontal?
So basically, does
it choose the force, or can it choose the direction directly?
So basically, the swimmers knows what it means horizontal and vertical. Okay, but now it will choose the action, so one among the 7 actions, following a policy. And now we will discuss how to construct the policy.
Jérémie,
yes,
I also have this out. So how you should apply the force in order to move it vertically or horizontally? I don't know.
So basically, so in order to swim vertically, the swimmers need to propagate a wave horizontally. Maybe I should go back to this thing.
So is the P perpendicular, which
exactly. So basically, if you propagate along the P perpendicular, it's creating a motion in the transverse direction.
Okay.
And that's just a solution to the Kosra equation here.
Okay. So essentially,
in the absence of fluid velocity.
So essentially, you can choose 2 different directions and the 3 values of alpha.
Exactly. So I can choose P perpendicular being EY, and then I will move in along EX, but then I can move left or right along EX. Okay, depending where my head is oriented. And then I can choose the reverse thing, which is P perpendicular along EX, and then I will have a displacement along EY. That's clear?
Okay. Yeah, thank you.
So so basically, one of the main difficulty of this kind of problem is that because of this high, this super projecting representation that we have decided, basically we are getting very far from Markov processes, and actually we are in the so-called partially observable Markov process, and for which we have to make a decision, and for which there are only very few results about the convergence of any kind of learning. So basically, so of course, the first trial that we have done is to use QLearning. So I will be quick on that. So basically, the idea is the following: is to say that so of course the agent is at time t is a given state that it's able to monitor, so you know in which state it is, and then it has to decide for an action A to perform up to the next step, which is t plus delta t. And then by performing this action, it's receiving some given reward, R of t, and then entering a new state, decide a new action, etc. So this is what we represent, and basically as a reward, of course, since we want to maximize the displacement to the right, I mean the reward at time t will be the displacement of the center of mass of the fiber between t and t plus delta t in the x direction. So you see the reward is negative if the fiber is moving to the left. So now the QLearning is just a proposal of an algorithm, which is to say that we want to maximize a given gain function that is called Q. So in our case, it's not a function, it's a matrix, because we are living on a discrete space, and this in such a way that we will choose A of t at time t as the value of A for which Q of S and A is maximal. And this we will do it with a given probability, 1 minus epsilon. And then with probability epsilon, we will choose any other which is different from this place where it's maximal. So in principle, these Q algorithm are able to define a policy and including a probabilistic policy, because we are not forced to follow exactly the maximum predicted by the Q matrix. So during the learning phase, basically Q will be updated following this equation, which is just a formulation of how to maximize Q. And basically, so in this algorithm, there are different parameters that needs to be tuned, and in particular there is the learning rate, which is telling us at what rate we are modifying Q, and the discount factor on which I will talk after. So basically, this learning rate, since we have a physical problem where it's quite easy to understand what will be the time scales, so we have chosen for this learning rate something such that it's associated to the typical time to travel by one cell during I mean in the absence of flow, of course. So it's the typical time to travel of a length equal to the cell size with the swimming speed that we have in the absence of fluid velocity. So now this discount factor is something which is actually entering in the quantity that is approximated by Q. So Q is actually quantifying what is called the expected discounted sum. So I'm sorry, I forgot to write some expectations here. So it should be the average of that. So which is basically the discounted sum of future rewards. So somehow a Q is after some n step is supposed to approximate the sum of the future rewards. So or the rewards at times n plus m, but with a kernel which is decreasing in the future. So basically, somehow it means that by tuning this gamma, one can choose either, if gamma is very close to 1, to try to maximize as much as we can in the future. But in that case, it would mean that in principle, the algorithm will never converge because it will need an infinite time to be able to probe an infinite future. And usually, so we use this parameter to be less than 1 in order to have a finite horizon to maximize. And in our case, so basically we have chosen this parameter. So 1 means infinite. So less than 1, but close to 1 means large. And so basically we have used a value of gamma, which is such that the associated time corresponds to traveling by 10 cells. So you see, so basically it happens when one is starting to play with this QLearning that there are hundreds of recipes on how to choose lambda and gamma, but here basically we can interpret them in terms of physical timescales, and this is something that I think is pretty important. But the problem is that there are very few results on the convergence of the QLearning to indeed the expected discounted policy, discounted sum of rewards, and what, the main theorem which allows you to know that the algorithm is converging, it requires to have lambda decreasing as a power law as a function of time. So basically, lambda has to decrease as a power law as a function of time, and basically epsilon also has to decrease as a function of time. Okay, so these are the two main ingredients in order to be ensured of the convergence of the algorithm. So here, what I show is the fact that indeed, this QLearning is not converging. So what I show here are just 24 different learning episodes, if you want, independent from each other, where basically each realization is just learning by itself. So what you see on these things, so here what is shown is the displacement inside the cellular flow. So you see that the fingers here are corresponding to different cells, and here for these 24 different initial orientations. So here I'm just changing the initial orientation. So the fibers are started straight and at the center of a cell. And then I'm just varying the initial angle it's doing with the vertical, and you see that this can have drastic impacts on the thing which is learned. So in particular, basically what you see when looking at the displacement as a function of time of these different 24 different realizations, what you see is that you have two behaviors. Some trajectories are having clearly a net displacement, so they move by more than 80 cells in the time 1000. So of course, some are performing much better than others. But then you have a bunch of trajectories which are just trapped, completely trapped, and they move, they stay there for a very long time. And basically, it's not that they stay there and they wait for something to happen in order to start moving. It's rather that they are learning something wrong. So they learn to get stacked. Okay. So which means, and typically this means that the convergence of your algorithm, so whether you will get some strategy which will allow you some displacement, or if you get trapped, is depending on your initial condition, which is clearly a sign that the QLearning is not converging. So in order to get some possible policy and to get rid of this kind of problem of convergence, so basically what we have done is to implement a genetic algorithm. So the idea is super simple, is that so we start different independent learning initially, so with different initializations of Q and different angles. And then after a long time, so I mean, this 1,000 time corresponds to having traveled hundreds of cells. Basically, you just pick among this generation of learner, you pick the one which is performing the best. Okay, and then you repeat this thing. So here it's repeated 12 times, and until you expect something which is close to a strategy which is maybe not optimal, but at least which is working, where the trapping is not occurring. So there are two remarks here. The first remark is that what you see is that I mean, on the long run, you can see that indeed there is a clear velocity which is emerging. So which means that we are learning at least with a notion of mean velocity. But the second thing that you can remark is that even after a long number of generations in this genetic approach, you still see that there is some spreading in the performance, and which is surviving forever. Okay, and because this is just due because here I mean the policy is barely changing, and the fact that you have this spreading is due to the dynamics itself of the fibers, which is chaotic. So I mean, this is another way to look at the convergence. So basically here what I'm showing is again as a function of the physical time. So here I mean in these units a generation of the genetic algorithm is lasting time 1000. So you see that you have your 12 generations, and here what is shown is some kind of sketch of the policy. So here on the y-axis are the 12 different states. Okay, and there on the I mean the colors corresponds to the different actions. So what you see is that after a time of the order of 5,000, 6,000, I mean the policy has converged. So there is no more change in the policy. Okay, because I mean the strips are not are constant. And what you see also is that everything is happening mainly at the very early stages of the genetic algorithm. So another way to look at the convergence is to look at the values of the Q matrix. I'm sorry, because I mean we have 12 states, so when need to look at 12 graphs, and on each graph, I mean they are the 7 actions plotted here. And so basically this Q matrix, so what you see for instance on this graph is that so this corresponds to state 0. So basically it's the first line on this array plot, and what you see is that clearly there is one action which is getting larger than the others, so the red one, which corresponds exactly to this red overpassing the other values of Q. And so there are some stuff which are clear, is that we are not sure to have really converged, because it seems that most curves are still growing. I mean, they have not reached any asymptotic values. Maybe these twos are closer to an asymptotic value than the others. And then for some states, so the so-called buckle states, basically we are really far from being able to say that we have any convergence, because you see the values of Q are much smaller than the others, and the detachment from the other curves is really less impressive. So the thing is that of course we could run things for longer and longer, but since we have no clear expectation concerning the convergence, basically it's the convergence of the values of Q. I'm not talking about the convergence to a policy. Basically, it might be just power consuming rather than telling anything interesting about the physics behind. So the one remark is that of course these states here, which have the buckle states, which have very low values of Q, are actually visited are not visited often, and this is another problem of the convergence of the QLearning, is that each state which is in your Q matrix has to be sufficiently visited. So visited enough when you make the n to infinity. Yes, Massimo.
But have you tried to remove some of the states? For example, the buckle state that are not
sure.
much visited.
So sure, we have removed some.
And doesn't change still the convergence.
It doesn't. No. So if you remove the buckle state, you will increase something I will talk about, which is trapping.
Okay.
So even if the state seems irrelevant because it's visited only a few times, if you don't know what to do, and if you look, actually what you do in this state is a bit different from see, if you compare, for instance, these two columns, they are just changing by buckled or not buckled. And you see that what you do is really different. Here you just swim like a mad to the right. So these are the things which are clear because you're facing the right direction and you have the flow in the right direction. So you just swim to the right. And here, if you're buckled, you see, you need to do something different. And basically, so I will talk about trapping, and actually, these buckle states are very important in order to prevent fibers to be trapped in a cell. So I don't know if there are. Certainly they are very important during the learning process, but then it could be that for some parameters of the cellular flow. And in the case where you just apply the policy without learning, that you can get rid of them. That this is possible. So here is how the optimal strategy is looking like. So here, it's learned. It's not learning. It has learned. And so what you see is that so the swimmer is trying to catch the place of the flow which are pushing it to the right. You see, so it's able to know that when it's facing in the wrong direction or in a place where it has a headwind. So except here, of course, it's doing some specific choice to avoid these things. So I don't know. I hope the network is fast enough so that you can see the movie. Okay, so basically, what you see from that is that an efficient way to move to the right is to do this kind of slalom between eddies, or to surf in between the rolls. You see, and this is something that you can see by looking, for instance, at this kind of stroboscopic map. So which is basically it's put back to two cells. So by using a periodicity of the cell, what is shown here is the position. Each point is the position of the center of mass during one travel. Okay, so basically each time it's so basically I'm taking a snapshot at equally space time, and each time I'm looking where is the center of mass. I fold it back to the periodic domain, and I draw a point, and then I'm drawing black point corresponds to having a large value of the gain of the reward, and the red points corresponds to low values. And what you see is that I mean, high reward really correspond. You see the trace of high reward there. So basically, it really corresponds to have this kind of slalom between eddies, or this kind of surfing trajectories. And red points are a bit different, because they correspond to being trapped along the vertical separations between cells. Okay, so here and then maybe and here, which corresponds to being a place where you're so this is a specific place which corresponds to having the head in the right place, but the body in the wrong place. So basically, your head is feeling that the wind is in the right direction, but your body is actually stacked because it has the wind in the other direction. So the thing is that the second thing that we have measured is how stable are these trajectories. So for that we have integrated. So once we choose this optimal policy, we have integrated the perturbation, I mean the linearized perturbation to our equation. So we take our PD and we just linearize the equation, and then from that we measure some kind of finite time Lyapunov exponent, which is obtained by the exponential growth rate of the norm of this perturbation. I mean, so the exponential growth rate of between two successive times of this thing. And so what is shown here is how this exponential growth rate is correlating with the reward. So here is the joint distribution of reward and exponential growth rate. And what you see is that basically large reward, which is this place here, I mean, place where the velocity is positive, so this is the x velocity, correspond to mainly to positive values of the finite time Lyapunov exponent. So the mean Lyapunov exponent is positive, so which means that indeed our dynamics is chaotic. But more interestingly, basically the place where you get a great reward, so which is on this edge of the PDF, corresponds to very unstable situations. So which means that basically, I mean, these trajectories here have a high Lyapunov exponent. And then the second remark that you can do from that is that here in this place here, you see that there is a significant probability somewhere there with rewards which are much smaller, okay, and Lyapunov exponent also which are smaller, and these correspond to the traps I was talking about. So which is the fact that from time to time your swimmer is entrapped in a given cell, and you see that you have this kind of red orbits, and which corresponds to exploring these regions here, and these regions are much more stable than the surfing trajectory. And so the question that we are trying to answer now, so basically we have no idea on how to prove it, is whether or not the algorithm, the genetic algorithm that we have chosen there corresponds somehow to among different strategies to minimize the Lyapunov exponent, I mean the finite time Lyapunov exponent, or the growth rate, if you want, which is associated to these surfing trajectory. So you see, I mean, if you slightly modify the policy, I mean, your surfing trajectories will not exactly look the same, and it could be that actually it will make them more unstable, so which means that this tip here, I mean, this stuff which is a signature of this surfing event will go up with a larger growth rate, and so which will make this kind of highly rewarding configuration much less stable. So which means that it's very likely that you exit it in a smaller time. Okay, so here now the next thing is that we have tried a bit to look at the robustness of this optimal strategy. So we have fixed the strategy, and then we have varied the physical parameters that we have in our model system. So on the left, we have varied the fluid velocity. So we have increased the velocity and decreased the velocity of the fluid. So what you see, of course, is that when the velocity of the fluid is 0, you swim with the swimming speed in the absence of velocity, and then things are decreasing. There is this kind of bump here, which is certainly related to the fact that fluid velocity and swimming velocity are becoming of the same order. And then at some point, you just go to 0 in a very abrupt manner, because if the fluid velocity is too large, you are not able to swim anymore to the right. And then here, what we have done is to plot now the dependence on the fluid cell size. So what is shown here is so on x-axis is the length of the fiber in units of the cell size, and again the swimming speed. So of course, when the cell size is infinite, so which means that you never sample enough space to feel really that you have a flow. So because the gradients are getting very small. So basically here you get a swing speed which is the same as in the absence of fluid. Then there is a minimum, and you see it's highly non-monotonic. It's another maximum and a maximum which seems to be higher than 1 for fiber sizes which are of the order of twice the box size. Yes, Massimo.
Yeah, sorry, I had the problem to unmuting. So a question. You have shown when you wrote the equation for the forcing,
yes,
that you enforce some specific relation between frequency and
yes, but that it doesn't really matter.
No, I mean, but changing the length, it means changing the frequency here.
No, because no, actually what I'm changing is the size of the cellular flow.
Okay. You change the size of the cellular flow, but I mean, in a way, the question remain valid, because I was thinking that what may matter is the frequency of the wave with respect to the typical time scale of the cellular flow. So when you change the size of the cellular flow and you keep the swimming velocity constant, you are changing the typical time scale. So it would be nice to see this figure in terms of frequencies, to see if there is some resonance.
Yeah, yes, it's comparable, because yes, of course. So I should have added in my parameters here, in my non-dimensional parameter, I mean, there is also the frequency that you put for swimming in units of U.
Okay.
But then yes, I was a bit quick on that. So basically, the swimming speed is almost always, you see, of the same order as omega divided by nu.
Okay.
Okay. So of course, I mean, it will be much simpler if we could solve the Kossera equation with this forcing in order to have an exact solution for the swimming speed, you see, like this as a function of the forcing amplitude, but we are not able to do it yet.
Okay, thank you.
Okay, okay, so now that we have tested more or less the robustness of this thing, so basically what we see from that is that if we want to see some displacement, we need capital U not to be too large, and also we need the land scale of the flow compared to the fiber land scale not to be too small. Okay, so basically we don't want to have too many eddies of sizes smaller than our fiber. And now, so the next thing is just a small test that we have done, which is now to put also the same fibers, but this time in a 2D direct cascade simulation. So basically, so we have two cases. So the case that you have just seen, where we have chosen this frequency we are talking about lesser than a given threshold. Okay, and then we have taken it larger than a given threshold, and clearly what we see is that in order to have some net motion, we need this frequency of swimming to be large enough, and which really correspond not to have u, I mean the local fluid velocity too large compared to the typical swimming speed. And so basically now we are trying to understand whether this transition is sharp, because I mean really for these parameters we have not seen any displacement. I mean it's the mean speed of the swimmers is really zero. Well, for this one, I mean it's clear that they are moving. And so the thing also that we do observe, which is something which is pretty funny, is the following fact. So maybe here I can show it easier. Yes. So you see that this bunch of swimmers here is pushed to the left by this eddy, and they tend to get packed together. And basically you see that they're creating some very filamentary distribution of fibers, so which means that clearly there is clustering. And here, I mean, on this side also, what you see is that you have, for instance, this bunch of swimmers which are following a path which is very similar from each other, and basically we were wondering if there is not, through the correlations appearing in the flow, some kind of ways to create some schools of swimmers. So just so I'm sorry I'm late. So just to quickly summarize and give some perspective. So basically what I was trying to show you is that this proxy of undulating fibers seems to be pretty funny in order to look at situations where one is willing to look at locomotion and navigations at a comparable scales. Then that the convergence of the QLearning algorithm is far from being granted, and in particular there is some interplay between non-Markovianity and chaoticity, which explain this large spreading in the realization of learning. But then, so it seems that we can overcome these things by using a genetic algorithm. But still, we want to understand further whether the selected trajectory through this genetic algorithm corresponds to some trajectories which are more stable than others. Then these deformable swimmers, when they are put in this simple turbulent flow, they seem to cluster and form some schools. So and basically, it will be very interesting to see if this can be used to increase performances. So, for instance, through hydrodynamic interactions, some repulsion, etc., some modification of the flow, and then. Of course, we are now going beyond QLearning, but it's ongoing, and we are trying to implement some interestingly random strategies, and in particular, we are playing with the actor-critic representation for this problem, so which is another way to tackle this learning issue, and of course, on longer term, basically we want to modify a bit the way we are modeling the active force, because actually when you think about a robot or some microorganism, basically it's the robot or the microorganism is not controlling the force, but rather the torque through the deformation allowed by its body. Okay, thanks.
Thank you for this very nice talk. Perhaps given the time, we can have one quick question and continue the discussion during the next discussion session.
I have a quick question. Can I ask? This is Luca from
Yes,
Rome.
please go ahead.
Can you hear me?
Yes,
yeah, sure.
Okay.
Hey,
ciao, Jérémie. Thank you for the talk. Nice, very nice talk. I have two questions indeed. The first, I mean, I apologize first of all because I followed the first part of the talk on the phone, so maybe I missed something. Maybe you already said. Do you have a baseline eventually to compare with? I mean, is it possible to imagine some, I mean, trivial policy to understand how much your algorithm?
Yes. So basically yes. So I have not talked about it because it was. I'm sorry. I cannot go back. Yes. So basically, the baseline, so the naive strategy that we investigated was something where so basically it consists in moving straight when the swimmer is facing the right direction and has the flow or no flow in this at its head, and then just to move vertically and not horizontally in all other cases. And so the thing is that basically it's a discussion which is related to chaoticity. This configuration seems to make the surfing event, I mean these things here, less stable. So even if it's this naive thing that you are thinking about, actually it's very more likely that you're trapped. So somehow what it means that you're able to go faster during these events, but these events will last longer, last shorter. Okay, you will escape these very benefic events in an easier manner. You see, that's. I don't know if I was.
So you clearly outperform this baseline.
Yes, but you outperform it only on very long time scales. If you just measure the instantaneous velocity over, I don't know, 5 cells.
Okay.
So it's likely that the naive thing will do better.
All right. Any other questions, comments?
Okay. And if I can, I have another question on the slide that you just show now.
Yes.
Okay. Yes. Please ask other people if they have other questions, and then eventually I pose my.
I don't see any raised hand. Please go ahead. Yeah. Professor Biffarelli, please go ahead.
Okay, so very quickly, I just was curious to know, when you say that you linearize the dynamics, you fit. Yeah, I was just curious to know, when you say that you linearize the dynamics.
Yeah, Luca, I don't hear you.
I think we lost.
Luca, you're on mute now, I think.
Yeah, Luca is lost. So maybe we can.
Yeah.